S. Chan presents Educational Video Lectures. Difficult concepts made easy. Study anywhere, anytime.
Hello students, in the previous video we have done that how operational amplifier can be used as a bistable circuit, how to make the calculations with the bistable circuit, and how the bistable circuits looks like. We have discussed the circuit parameter, that how the changes can be done in the input and how we make the calculation so that the operation amplifier will act as a bistable circuit. We have discussed the positive saturation, we have discussed the negative saturation, we have discussed the transfer characteristics during the positive saturation and the transfer characteristics during the negative saturation, and then we have calculated the total transfer characteristics, which includes the positive saturation as well as which includes the negative saturation. For the both positive and the negative saturation, we have made the how to make the particular calculation.
If you want to study this topic in detail, refer to the book by S. Chan Publishing. Link is provided in the description box.
Welcome to S. Chan Academy. My name is Kanhaiya Jha. Now, in this video, we'll learn more about the bistable circuit as a comparator. As we can see the hysteresis comparator characteristics by rejecting the interference, that it will generally reject the particular interference in the particular signal, and by using this we'll calculate the hysteresis particular characteristics. Hysteresis characteristics is generally calculated because we are using the RC circuit in this. RC circuit that will include the loss factor. So due to loss factor, distortion will happening in the particular amplification. So rejecting that particular the particular part of the distortion will make the operation amplifier will work as a bistable comparator. So it will reject the particular values of the rejection or the values of the distortion in the particular oscillating values. We can see here, if you see here, that you can see that the curve portion and this one. So basically the signal which need to be overlapped during the zero crossing, and this is the clean signal and this is the interference happening. So it will reject the signals which are not required or which are distorted or which are not giving the correct value, or from where we are not getting the particular application or the particular uses. So this is basically the main role of the bistable circuit, where we can see here that the output level here, the output level will become more precise. As we can see here that this is the op amp that we have made, this is the particular positive and the negative, and then we connected R1, R2, and this is the R. Here we are using the two diodes. As you can see here, the Zener diode are used, the Z1 and Z2 are a Zener diode 1 and the Zener diode 2, and then they are grounded. So for the positive saturation, we can see VZ1 plus VD, and for negative saturation VZ2 plus VD, that will be negative. So VD is the forward diode drop. So again we can see here that how the circuit is generally analyzed, how we are making the calculations with a particular circuit, how it is connected from the particular one input to the output, and then we are calculating this. We can see here that R1 and R2, the same way we have make the circuit, only changing that in the V0 we using the two particular Zener diodes, and from that particular Zener diodes we are calculating the positive saturation, and as well as we are calculating the negative saturation. We are calculating the positive saturation as the variation is going on, and in the same way we are calculating the negative saturation also in the particular circuit. So the formula that can be calculated is L for the positive saturation VG1 plus VD, and then for the Z2 we will use VG2 plus VD. You can see here that their biasing is different. When we are using the two particular diodes, the G1 biasing is different and the Z2 biasing is different. They are basically in the opposite biasing to each other. That G1 is connected in the different biasing mode and the G2 is connected in the different biasing mode, and we are calculating this. So general diode 1 in a different biasing mode, general diode 2 in a different grounded mode, and then R1 and R2. So we are calculating the positive saturation, and here we are calculating the negative saturation. So we are calculating the positive saturation and negative saturation in this. Coming how this circuit gen used as a comparator. Comparator where the strong signals, weak signals, or clean signals, we say distorted signals, where they can compare and then reject the particular distorted signal. So what we will get in the output will be a clear signal which will give us the output. We will not get any particular signal in the output that is basically distorted, that we cannot use it. So basically comparator is comparing the particular signal with the weak values or distorted value, or the signal which can make an intersection in spite of overlapping, it can make an intersection. So here we can see, that this particular circuit is generally used here, and this particular circuit we can use that again coming back to the general diodes, that the voltage comparators, the one is used in this way and the another one is grounded. Okay, in the particular operational amplifier we are making the connectivities like this, and when we make a connectivity like this then it will vary accordingly. So in this we can calculate here the positive saturation, we can calculate the negative saturation, we can calculate the positive saturation characteristics or the positive transfer characteristics, we can calculate the negative transfer characteristics, and we can also calculate the total transfer characteristics. So the circuit as a bistable mode enables us, the operation amplifier, to identify the particular signal, in terms of which signal is required and which signal is not required. Which signal can go for the overlapping and we can get the output, which signal cannot go for the overlapping, and in spite of overlapping they can go for the intersection of the particular signal. So when they go for the intersection or when they intersect with the value with each other, in that case definitely we cannot calculate the output. So we can see here that how for the particular output we are again using this rotating this value to get the output. So this characteristics of the operation amplifier enables the amplifier to work as a circuit where we can select the particular signal, where we suppose, take an example, when we are passing from somewhere in the hospital or from the defense area, we see that our mobile signals are not working, and again we cross that area, then the signals are working. Again we are making this, that we will not get the signals which are not required there we are blocked. The signals which are not required we will not get that, the signals which are required we will get only that. So the positive saturation is this, how we calculate. The negative saturation is that how we calculate. We can calculate the particular transfer characteristics for the positive one, we can calculate the transfer characteristics for the negative one, we can calculate the total transfer particular characteristics also, that how we are making the changes in the particular operation amplifier and we can making it, so we can calculate that also. In this we learned here that how the particular operation amplifier can be used as a comparator. Now we'll take a small break and then continue.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back, students. As we have done before the break, how the operational amplifier can be used as a bistable mode and how we are calculating the particular transfer characteristics of the circuit and how we are calculating for the positive saturation and how we are calculating for the negative saturation. So we'll proceed further and now we'll discuss about the particular uses. So making the output level more precise, we can use this bridge. You might have seen this particular bridge in your lower classes. So we are using this bridge rectifier here, and you can see we are connecting this particular input. So we are making the particular output more precise. So for this circuit L positive, for the positive saturation it will be the Vg plus Vd1 plus Vd2, and the second one it will be Vg plus V3 plus V4, that will be negative. So here we are using D1, D2, D3, D4, we are using it, we are calculating it for the positive saturation as well as we are calculating it for the negative saturation, that how the positive saturation can be calculated. So we are taking this as a particular amplifier where we are using calculating the bridge in the output. So in a very simple way we can see that this is the particular op amp that we have. So these are the two particular inverting and non-inverting modes, and here we will calculate the particular output. So here we can do is we can connect the bridge here. This bridge, suppose that we are using this as a 1, 2, 3, 4. So the 1 and 2 will work as a for the positive saturation, and the other two will work as a negative saturation. So we are using this to get more precise form of the output. The output will be more defined. The saturation characteristics that we are calculating, either for the positive saturation or for the negative saturation, that will become more defined and we will get more accurate values from this. If you see this particular slide again, we can see this, we are using this, okay, and in between we are using this Zener diode. So this Zener diode is generally used. So we are using this L, the positive saturation Vg plus Vd1 plus Vd2, and for the negative saturation it will be minus Vg plus Vd3 plus V4. So we are using this particular calculation values, we are using this again and again to make the output more precise. Either it is for the saturation, positive saturation, or it is for the negative saturation, or it is for the total transfer characteristics. We can calculate any of this very particularly in our calculation. Then we will move to the particular circuit which is the generating a square waveform. Square waveform, as we have studied in the lower class, it will be basically the conversion from the analog to digital, that how we generally come to the digital value when we are starting with the particular analog value. So connecting a bistable multivibrator with the inverting transfer characteristics in a feedback loop with a RC circuit results in a square waveform. So when we are connecting it bistable multivibrator, okay, with any particular RC circuit, we can see in the RC circuit here. So in the RC circuit will generally gives the particular square output or the particular output which is required to in the digital form. So we again analyze that how the operation amplifier we studied as a bistable circuit, then we study as a make a circuit that will give us a defined output by connecting a bridge in the output. After connecting the bridge in the particular output, we can see that how it will work as a multi-vibrator circuit, and when the operation amplifier as a bistable mode using as a multi-vibrator is connected to the RC circuit, then we can give the input in the analog form and we can get in the digital form, or we can see that we can give the sine wave in the input and we get the square wave in the output. Where we can see here that there is the no time period for this. Here is the starting initial point and here is the final point. There is no time period concerned in this, but here we can see the time, the pulses, the pulse rise, the pulse duration and the pulse fall. So in the output that we are getting is purely in the square form or in the digital form when we are starting from the input. The input is basically in the sine wave and the output that we are getting is basically in the square wave. So this is the particular operational amplifier which is generally used as a generating the particular square wave. We have studies how the operation amplifier can be used as a bistable circuit. From the bistable circuit we have learned that how we have to do the calculation, which inverting and non-inverting, depending upon the positive saturation and depending saturation, the calculation that we have to do, what kind of changes that we have to do in the particular legs, and how we are calculating the particular output in all these particular cases. So basically, when we connect or make the output as a bridge rectifier, then the operational amplifier as a bistable circuit is connected to a multi-vibrator, and after that what will happen is, if we give the input signal as a sine wave, we will get the output signal as a square wave. So if the input given is analog, then the output can be calculated as a digital. The circuit will move like this. Again I repeat, where we can see that we are calculating the total transfer characteristics in this. In the total transfer characteristics in this, we are calculating the L plus and the L minus, both L plus and the L minus. And when we are clubbing both L plus and the L minus, then we can see that this is connected with the RC circuit and becomes a multi-vibrator where it has the ability to give the digital signals. So nowadays we understand that whatever we want has to be digital. It has, either it is a watch or it is a toy, whatever. So basically a simple op-amp, the ideal circuit that we have discussed in the previous slides and the videos, that what exactly the ideal particular op-amp was, how we make the change in the ideal op-amp, and after making the changes in the ideal op-amp, then how it is or it can be used to give the particular square waves or the digital signal in the output, that whatever the variation that we do in the input, or the sine wave that we give in the input with the square wave will given in the output, when this will be connected to a particular RC circuit. RC circuit, as we can see, the resistance and the capacitive circuit. Then we have generation of the square waveforms. We can see this particular circuit when it is connected to the multi-vibrator. We can clearly see that it is connected to a multi-vibrator and it is connected to the RC circuit. That the transistor first has to be made in the bistable mode. After making in the bistable mode, we can use a bridge rectifier that will make it as a multi-vibrator, and then it is connected with the RC circuit. So when it is connected with this RC particular circuit, then it has ability to give the digital signal. So whatever the signal that we give in the input, whatever type of signal, either it is a sine signal or whatever, in the output will give a digital signal in this. So here we can see that. Now the waveforms at the various mode of the circuit, we can calculate. The circuit is a stable multi-vibrator. We can see the total time is equal to T, which is T1 plus T2. So total time here is T, which is T1 plus T2. So we can see here that how we are getting the positive saturation, how we are getting the negative saturation, then how we are calculating the gain in each factor, the beta L plus and the beta L minus. We are calculating the time constant CR, and then we are making this particular calculation. So waveforms at various nodes of the circuit is given. The circuit is a stable vibrator where T is a T1 plus T2, where T1 is equal to RC. We have log value 1 minus beta I saturation, positive saturation over negative saturation 1 minus beta. In the same way, we will use this particular value over the 1 minus beta, positive saturation over negative saturation 1 minus beta. So this is the value that we are getting, that T is equal to 2 RC log 1 plus beta and 1 minus beta. So here we can see that if the op-amp, the operation amplifier, we make it a more defined output by connecting a bridge in the output, then how it can be work as a multi-vibrator, and when that connected with the particular RC circuit, then from the RC circuit how we are getting the digital waveforms or the square waveforms in our calculation. So we are calculating this in all these particular values, the digital waveforms and all that. And then we have the triangle waveform. This is the operational amplifier. This is the saturated state. There is a resistance, this is the capacitance that we are using. Again, you can see that we can use using the output, the saturation, the V L plus and the L minus, here L plus and the L minus, and we are getting the digital form. So this is the Y-stable mode. So we can see that we are getting the, again the output in the triangular form. So we are getting the output in the square waveform, we are getting the output in the triangular waveform in this. Then generation of triangle waveform we have discussed in the previous slide, this is the L plus and this is the N minus. This is the particular pulse value that we are using. This is the particular pulse T1 and T2. So the gap, so depending on T1 and T2, so this will be the T1 and this will be T2. So the value of the T1 is this pulse and the value of this T2 is this gap pulse. So we can see here, this is a T1 and this is a T2 where we are having a triangular waveform. So in the output, we can have the triangular waveform. In the output, we can have the square waveform or a digital waveform as it is required. So depending upon this, we will make the changes in the particular input. The way we make the changes in the particular input will get the particular output. So here we can see here that we are getting from the sine wave, we are getting the triangular wave also. From the sine wave, we are getting the particular square wave also. So connecting the particular op-amp in the output, we are with a bridge, we are making it a multi-vibrator. Connecting that with the particular RC circuit, we are getting the particular square wave also, and we are getting the particular triangular wave also. So in a very summing words, what we can say is that in the operational amplifier, from the ideal one, we make changes, we make it as adder. Again, we use to operational amplifier, we get a summer. Then we can use as an integrator depending upon integrating the particular inputs. We are using it as a differentiator when we are differentiating the particular inputs, as we have seen V di by dt. Then we can use as a bistable circuit. From the bistable circuit, we can make it as a multi-vibrator, and from the multi-vibrator, how we can see that it can use as a comparator, that it can reject the unrequired signal, and it can also use to change the particular signal, that in case in the input we are having a sine wave, in the output we can have the square wave, in the output we have a triangular wave like this. So the intention of this particular op-amp module was to make you understand that how we make a simple op-amp, how we are making changes in the particular op-amp. The changes like this from the ideal op-amp, how we club the input in one leg, how we are making inverting and non-inverting, how we are making adder, how we are calculating for the integrated value, how we are calculating for the differentiated value, and most important, how we are calculating it for the positive saturation, negative saturation as a bistable circuit. From the bistable circuit, how we form a multi-vibrator, and then from the multi-vibrator, how we are using this particular op-amp to calculate the different signal waveforms. Like in the given sine wave, how we are getting the triangular wave, how we are getting the square wave and all. So hope the knowledge of the operation amplifier has been enriched and you have enjoyed this video. Thank you.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe. And do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.